Okay, but electron configuration is pretty simple. It's just a way to write how electrons are distributed in the atom's shells. Okay, so we talked about how electrons fly around the atom. They are in these shells. Electron configuration is a way to describe where they are, where the electrons are located. All right, now when we talk about electron configuration and where electrons are, we talked about shells, right? How do we know what shell an electron is in? How do we know that based on the periodic table? Yeah, exactly. The shells are based on what row that element is on, right? So we count the rows. If it's on the third row, it has 3 shells. We're pretty familiar with that. But today we're going to talk very briefly about something called subshells. Now, subshells might sound complicated, but it's basically sections of the electron shell. So they're divisions inside of a shell. So it's like a shell within a shell. Okay. In AP Chemistry, we talk a little bit more in detail about this, but for this class, just know that in a shell, there are sections where the electrons tend to hang out more than other sections. Okay. And when we write electron configuration, that's what we communicate. We're going to communicate what shell the electron is in, and then what subshell. And there's a notation for that, which I'm going to show you guys right now. But just know that's what a subshell is. It's just a shell inside a shell, pretty much. Okay, so there are different subshells, and just follow along with me for now. It'll make more sense once we actually start doing the problems. But basically, all of the electrons that are in this section right here, first 2 columns, and including helium, so if you want to make a note, helium, okay, these electrons are called the S subshell. S subshell. Okay, and again, this might be a little confusing, but just go with it for now. Once we do the problems, it'll be a lot easier. Like, you'll understand what it means. Okay, so first 2 columns and helium, this describes the S subshell. All right, now this section right here, this box, is going to represent something called the P subshell. Okay, it's basically just another subshell. We call it S and P. They're just like the designations that we have. Okay, so if an electron is found in this area, it is called, it's in the P subshell. All right, the middle section right here, the transition metal section right here, this is called the D subshell. Okay, and you can ignore the ones here at the bottom. We're not really going to look at them. But if you want to know, this is the F subshell, but we're not going to be looking at the F subshell at all. Okay, so all you need to know for your exam, first 2 columns and helium are the S subshell. This middle section is called the D subshell. And then the P subshell is this right section. Okay, pretty easy rectangles to remember. All right, guys, so like we said, electron configuration is a way of writing and communicating where the electrons are in the atom. So we're going to go over how to write that configuration. Okay, so every element has its own configuration, and I'm going to show you guys how to do that. So we're going to start very easy. We're going to start with the first element, hydrogen. Okay, so we're going to be looking at this guy right here. Okay, so hydrogen's electron configuration is very easy. First thing you do is look at what row it's in. Hydrogen's in row 1, right? So first we're going to write number 1. Okay, to communicate, it has 1 shell. It has an electron in the first shell. And then if you look at hydrogen, which subshell area is it in? S. Yeah, we said this section right here is called S. So it's going to be 1 S. Okay. And if you look at hydrogen, it is the first box in that S subshell, right? So the configuration is 1s, and then we put an exponent 1. So the way you would read this is 1s1. Okay, super easy. So today you're literally just counting the rows, figuring out the S, P, D subshells, and then counting the boxes. Okay, so we'll do a lot of practice today just because it'll make it a lot easier once we do it. Okay, but we'll go on to the next element, which is helium. Okay, so helium right here. Okay, so what row is helium in? 1, so it has an electron in the first shell. Helium, we said, is the exception. It's also in the s subshell, so it's 1s as well. But if you look at helium, it is box number 2, right? So its electron configuration is 1s2. Okay? And that communicates that it has 2 electrons in the 1s subshell. Okay? Yeah. It is. All right, so far so good?
Are we allowed to bring it out?
No, I'm gonna give you a blank one.
But it won't have anything.
Yeah, it'll just be a blank periodic table. Just like this. All right, let's move on to the next one. So first row is really easy. Things change a little bit when we get to the lower rows. So we're gonna look at lithium. Okay, so Li. Okay, lithium is right here. And if you look, lithium is in the second row, right? So the way that you do electron configuration is you're communicating all the electrons in the atom. So that means that lithium has electrons in the first shell, right? So we just look right here. The first shell has 2 boxes, so we copy down 1s2. Because to get to lithium, we have to count these boxes. So 1s2. If you look at lithium, it's in the second row, right? So we're gonna put a 2. What subshell is lithium in? S. So we put 2s because it's in this section right here. Everybody right here is in the S subshell. And if you look, which box number is lithium in the S subshell? 1. So it'll be 2s1. Okay. Yeah, you need to include the 1s2 because to get to lithium, we have to go past hydrogen and helium. So you include that in the configuration. Yeah. All right, so I'm going to slowly have you guys try one on your own, and then we'll go on to the more difficult ones. I want you guys to try Be, beryllium. So let's do the next box, beryllium right here. Write the electron configuration for beryllium. Okay, guys, so if we take a look at beryllium, you'll notice it's the box right after lithium, right? And if you look at the pattern, if you notice, we're just adding on to what we have, right? So for hydrogen to helium, we just changed the exponent to 2. Lithium, we kept 1s2 and we added 2s1. So if you look at beryllium, we're just going to build off that as well. To get to beryllium, we need to go through hydrogen and helium. So we're going to write 1s2, and then we're going to build on top of it. If you look at beryllium, what subshell is it in? S. So it's going to be 2s, and box number 2, so it'll be 2s2. Okay, so if you notice, we're just adding on to what we already have. The exponents are just going up. Okay. All right, I'll show you the next one, and then let's see if you guys can try the one after that. We're going to do boron now. Okay, so boron. All right, so if we take a look at boron, same thing as before. To get to boron, we need to go through all of these other boxes, right? So same thing as before. We need to get through hydrogen and helium. And to get through that, we write 1s2. Okay, we need to get through lithium and beryllium. And what subshell do we say this section is? S. I know I keep asking you the same question, but I'm really trying to drill it into your brains. Okay, so it's going to be 2s, and then there's 2 boxes, so 2. But if you look at boron, what subshell is boron in? P. It is in P. This section right here is all P. So here, we're going to change from 2s, and then we're going to change it to 2p. It's box number 1, so it's going to be 2p1. So that's the pattern. Okay, so once you move to a new subshell, you don't change the exponent. You go on to writing a different subshell. Okay, so if you take a look at nitrogen, same thing as before. It is in the 2p subshell. Okay, so nitrogen is in the 2p subshell. So we're going to keep everything that we had before. Okay, so H and He, that's going to be 1s2. We go through lithium and beryllium, that's 2s2. Second row, P subshell, so it's 2p, and nitrogen is box number 1, 2, 3, so it's 2p3. So this right here will be your complete answer. That's an electron configuration for nitrogen. Okay. All right, is it starting to make sense a little bit? Hopefully it's not too bad. It's literally just counting boxes and counting rows. Okay, let's have you guys try another one on your own. We're gonna go down a couple rows. We're gonna go down. I want you guys to try. Let's do sulfur. Okay, so see if you can work with the person next to you. See if you guys can write the electron configuration for sulfur. I'll give you a minute to do that. Okay, so for sulfur, we got to get to box number 16 right here. Okay, so we got to get through everything before it, right? So if we look at hydrogen and helium, that's 1s2. We kind of established that a couple times. To get through lithium and beryllium, that is 2s2, so 2s2. We got to get through this entire P section right here, so that's 1, 2, 3, 4, 5, 6. So that's 2p6. We didn't talk about this section though, but this is row 3, right? So this is 3. What subshell is this? S, so 3s, 2 boxes, so 2. Okay, this is the third row, but what subshell is this? P, so it's 3p, box number 1, 2, 3, 4. If you got that, great job. Yeah, you can give yourselves a round of applause. Yeah, they can get really long depending on what row they're in. So for the D subshell, let's take a look at Fe. Okay, we're gonna look at Fe. We're gonna do this one together, and then I'm gonna have you guys try one on your own. Okay, so the D, it's gonna be in the D subshell. We're looking at iron, Fe. All right, same thing as before. Yeah, what's up? 3s2 right here. Yeah, to get to sulfur, we got to get through this section right here, right? Third row, so 3. This entire area is the S subshell, so 3s, and then it's 1, 2 boxes, so 3s2, and then we got it. Then we can get to the P section right here. Yeah. All right, so for Fe, same thing as before. We got to get through everything before it. Now, some of you guys might actually start seeing the patterns, right? So you can just kind of skip a lot of it. So first row, 1s2. This section right here is going to be what? 2s2. This section right here is 2p6. This section right here, 3s2. Yeah, we're in the third row still. And then this section right here is 3p6. Okay, now we're in the fourth row, which is where Fe is. So K and Ca right here. What subshell is this? 4s. So we would write 4s what? 2. Good. Everybody good? Yeah.
So is S always just 2?
Yeah, pretty much. If you get past it. Now, if I told you to give me K, then it'd be 4s1.
Oh, okay.
But if you go past it, then it's 2. Exactly. All right. Now, D is a bit of an interesting subshell because when you look at the D subshell, there is a special rule. And don't ask me the reason why. We talk about in AP Chem. But for the D subshell, you actually need to drop the number by 1. So if you take a look right here, Fe is in the D subshell, and what row is it in? 4. So you would, naturally if we follow the pattern, we would write 4D, right? But for all the D subshells, when you get to the D subshell, you drop the number by 1. So it's going to be 3D, and that's the key to keep in mind. 3D. Okay, 3D. Okay, the TLDR, the quick explanation is once you get to these elements, their shells are really big, and so these electrons actually start going under the 4s subshell, and so that's the reason why. We talk more detail in AP Chem if you want to take it, but just know the D subshell, you drop the number by 1. Okay, and then Fe is box number 1, 2, 3, 4, 5, and 6, so it'll be 3D6. Yeah. Just the D subshell. Okay? Now, if you, like, let's say I asked you to find BR. This is in the P subshell, right? So it would still become 4P. But just the D subshell, you drop the number by 1.
All the way
Okay.
from.
Yeah, just 1. Just D. Alright. Make sense? Okay. I'm going to have you guys try one long one on your own, and then we're going to go over two new concepts. But this one I'm doing to kind of prove a point. I want you guys to do silver, AG. AG. Okay, guys, so let's go over AG. I'm sorry, I'm trying to prove a point, but it is very long. So I'm going to go through it very quickly. If you take a look at AG, it is in row number 5, right? And so we got to get through all of the other rows before it. So for AG, you're going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because remember the D subshell, you drop it. And then you go back up to 4p6, and then you get to row number 5 finally. You'll do 5s2, 4d9. If you got that, great job. That's about as hard as it's going to get. Okay, but you guys see the issue, right? This is stupid long, and it's a lot of writing. So there is a different way to write it. So up until this point, we've been writing something called the electron configuration. But chemists are really lazy, and this is just too much writing. So instead, most of the time, what we use is something called the noble gas configuration. Okay, and the noble gas configuration is a way of abbreviating the electron configuration. Okay, so noble gas configuration. This is the one that I'm going to show you guys now. So the noble gases are a type of element. They're found in this last column right here. Okay, they're called noble gases because they're something called inert. Basically, they are very happy on their own, and they don't like to interact with other elements. They don't like to react. Now, the noble gases are elements that have no MCI. If you guys remember, this is the no MCI section. The reason why is because they're already complete. So these are very stable elements. So we use this kind of as a standard for electron configuration because these guys don't change. They don't form ions. So what we do for noble gas is we look at the element we are writing, and we just go backwards until you hit a noble gas. So we go all the way back, and the noble gas right before Ag is krypton right here, right? So instead of writing all the stuff up to krypton, we can abbreviate everything before the 5th row. So all of this, and we can just write in brackets Kr. And then we just copy down what's in the 5th row. So 5s2, 4d9. And that's it. That is another way to write the electron configuration. A lot easier. Just skip to the noble gas, write it in brackets, and then just do the row that the element is in. Yeah, what's up? Noble gases they have complete shells, so it's just the classification. Yeah.
Why did you show this?
Because I want to prove a point. Yeah.
Is both going to be on the test?
I haven't looked at the test in a long time, but I believe you can choose. Yeah. On the assignment, you have to do both. I'm looking at the assignment right now, but for the exam, I believe I'll let you choose which one you like. Yeah.
Do you get the same exam every year?
No. Okay. So, just to finish up, let's do one last one, and then I'm going to show you guys the last thing for today, and then we're pretty much done with the unit. So, I want you guys to write the noble gas configuration for, let's do cesium, CS. Okay, should be really quick. Okay, I want you guys to write the noble gas configuration for cesium. If you want to do the electron configuration, knock yourself out, but I'm only going to give you a minute to do this. So, do the noble gas configuration for cesium, number 55, bottom left. Okay, guys, so cesium is really easy. What is the noble gas before cesium? Yeah, xenon, right here, Xe. So we put Xe in parentheses. This is row number 6. Okay, what subshell? S. What box? 1. That's it. Easy peasy. So up till this point, we've been looking at neutral elements, right, where they have all their electrons. But this unit, we've been talking a lot about ions, right, where they can become positive or negative. So I'm going to show you guys how to do the configuration for noble gas. Sorry, not noble gas, for ions. From now on, you can just do the noble gas configuration, but I'm going to show you guys how to do both. Okay, so let's do an ion together. So the first one I'm going to do is we're going to do, let's do Me, so oxygen. Oxygen's most common ion is 2 minus. So I'm going to show you guys how to do O2 minus's noble gas electron configuration. Excuse me. I'll also show you the noble gas one. Okay, so if you look at regular oxygen, actually take a second. I want you guys to do the electron configuration for oxygen. You can do regular or noble gas, but do it for regular oxygen first, and I'll show you guys how to do the ion. All right, so if you take a look at oxygen, I'll do both configurations for you. Regular is going to be 1s2, 2s2, 2p4. Everybody good with that? Noble gas configuration, the one right before oxygen is helium. And so you just write 2s2, 2p4. So for this one, it's not replacing a lot, but yeah. Okay, everybody good? Okay, now oxygen's most common ion is O2 minus. Now let's look at this 2 minus. If it's 2 minus, what does that mean? What does this 2 minus mean? Yeah, gaining 2 electrons. So what we're going to do is we're going to take a look at the electron configuration. We're just going to add 2 to it. So if you look at oxygen, if you look, 2p is the one that's the rightmost. It's the last one. So it's going to be the exact same thing as oxygen, 1s2, 2s2, but we just need to add 2 electrons to the last one, so it'll be 2p6. That's it. So if you want to do noble gas, it'll be this right here. So if you get an anion, a negative ion, you just add it to the last one. Yeah.
So basically for the MCR, that you just skip to the noble gas section.
You can also do that. Yeah, you can skip to a noble gas. Yeah.
How would you do the noble gas for like a gas already? Wouldn't it technically be like
Noble gas for...
Since oxygen is a gas.
Okay, so it's really easy if it's a negative ion. It's also easy if it's a cation. So we're going to take a look at another one. I want you guys to do the electron configuration for sodium, Na. Okay, do that real quick, and then I'll show you guys how to do it for its most common ion. Okay, guys, so sodium's pretty easy. I'm going to do the noble gas configuration. It's Ne, and then this is third row, so 3. What subshell is it? S, which box? 1, perfect. All right, now, Na's most common ion is Na+. If you have a plus, what does that mean? You lose an electron, right? You lose 1 electron. So, from sodium, we take away this electron, and remember, if a shell becomes empty, it disappears. So Na+ is really easy. It's just bracket Ne. Okay. Also, for oxygen, if you look, 2s2, 2p6, this is the same thing as Ne, right? So you could also just put bracket Ne for this one as well. So the ions are really easy because you just basically find which noble gas it goes to and just put that in brackets. That becomes this noble gas configuration. Okay, and that's it. Yes.
Is that kind of how it's like you do the ion first?
Yeah. Sorry, one other question? Yeah.
I'm confused because
Ne is after oxygen.
Yeah.
So regular oxygen, it's going to be the 2p4, but its most common ion, you gain 2 electrons, right? So if you gain 2 electrons, you go 2p5, 2p6. 2p6 is the same thing as neon, so you can just write neon as its noble gas. Yeah. There is one exception, though, with the ions, and this is what's going to be on your exam, so just letting you know. It gets a little weird with these transition metals. So we're going to take a look at, let's say, chromium right here. Okay? All right, I want you guys to take a minute, do the electron configuration or noble gas configuration for chromium. Okay, do chromium. This will be our last example. Okay, guys, so chromium, pretty simple. The noble gas before it is argon, Ar, so we would put Ar in brackets. Okay, this is row 4. What subshell is this? S, so it'll be 4S. How many boxes? 2. What about chromium? What is it going to have to finish? It'll be D. What row? What number do we put in front of D? 3. Yeah, it's lower than the row. And then it's box number 1, 2, 3, 4. So chromium is 3D4. Okay, so far so good? Okay. Transition metals, though, are a little weird because when you get their ions, it won't take you to a noble gas. Okay, because there's a reason why, and if you want to know, you can take AP Chem, but it's a little weird rule. So let's say we're taking a look at Cr+. Okay, Cr+. All right, if you look at the plus sign, what does that mean? Did you gain or lose an electron? You lose an electron. Okay, so it might be very tempting to be like, oh, it's going to be 3D3, right? But that is not the case. When transition metals, the ones in the middle, lose an electron, and you might want to write this down, transition metals, okay, they lose the S subshell first. Okay, so you're going to take away the electrons from the S subshell and then the D subshell if you have to. Reason why? The 4S is technically a higher energy level, so it's easier to take that one out. Talk about that AP chemistry if you want to know more. But for now, to solve the problem, just take it away from the S subshell. So chromium plus is still going to be Ar, so we're going to keep Ar. And you're going to take one electron away because plus 1, so you take it away from the S subshell. So it'll be 4S1 3D4. Okay. And again, that's the last rule. The last thing we're going to talk about for this unit. Transition metals, you take away from their S subshell first. If you need to take away more, then you can start taking away from the D subshell. But S first and then D. Just for the sake of example, let's say that we have a Cr3+. Then you would take away 2 from the S, right? So you would have Ar, but since you already take away 2, you need to take away 1 more. Then it'll become 3D3, but you would no longer have the 4S.